Good afternoon. Thank you for joining us for a security talk. I know there's other presentations going on discussing exciting functional things you can do with Android, but as I'm sure you realise, security, mobile app security is a very important topic. I'm Neal Michie. I'm Product Director at a company called Pace Anti-Piracy. We're a software security company. And I'm here today to talk about how, if you get in front of API security, you can become the hero to your DevSecOps team. Maybe a slightly strange thing to say, kind of where does mobile fit into the whole DevSecOps security? But as we go through this, hopefully it will start to become clear. So let's just step back slightly and set the scene. I appreciate most of this you understand already, but it's important just to set the scene and know where we're at, where we're coming from. So most apps, dare I say all apps these days, are going to be talking to server-side backend. And that server-side backend is providing services, it's providing data, and processing data you're collecting on the mobile side. And it's considered business-critical infrastructure by your CISOs, the Chief Information Security Officer, and the security teams that work under them. Where does the API come into this? Well, your app accesses these services through an API. So your app has a doorway, a gateway into that back-end server. So far, so good. Now, the danger of providing a doorway, providing a gateway, is it's prone to abuse. And API abuse is of high concern to pretty much any security professional. If you talk to a CISO of a large organization, you talk to security architects, the DevSecOps team, and you ask them to list their top concerns, API abuse is always in the top two. Any discussion I've ever had with these professionals, API abuse is always number one. If not, it's number two in their concerns and what they're worried about. And that's why they spend billions and billions of dollars or pounds or euros each year building defences that they build behind the API in the server side. And these defences are all about catching rogue usage of the API. And probably the most common, most well-known example of rogue usage is SQL injection, where you use bugs in the software to get the API to do something it was never designed to do. So well used by the bad guys to get into infrastructure through the doorways that we're opening to what should be legitimate application, legitimate usage. So how do we stop the API abuse? Well, as I said, the traditional way that the security teams operate is to build defences in the server side. So they're firewalls, the intrusion detection systems, kind of the usual buzzwords you see around security. But all these server-side defences are doing is they're monitoring the traffic and they're looking for things that don't look right, data passing through that API doesn't seem quite right, doesn't feel quite right. And the reason they work that way is because all they have to go on is the data. That's all they see, the data passing through the API. So they have to make go, no-go decisions based on what's passing through. So what I propose, and where this front of API topic comes from, is if we can extend our security perimeter out from the server, augment what it's doing with client-side security, and actually authenticate every client-side device, every app that's connecting to the API. And by doing that, we know it's coming from your mobile app, allow it through. It's coming from a script running on the bad guy's laptop, we stop it. And I've seen data that says simple but effective client-side authentication can stop API abuse. It can stop the bad actors connecting to the API to the extent that when you implement it, they've seen 80% of the network traffic disappear overnight because the bad guys are no longer connecting. That's 80% of the traffic they discovered was actually malicious. Never mind the security. Just think of the cost of processing and rejecting all that traffic. You can stop it immediately. Don't let it connect. You have a much more performant system and a much more secure system. So how do we do client-side authentication? How do we validate who's connecting and who's not connecting? The oldest trick in the book, the oldest approach, is API keys. I'm sure. Let's have a show of hands. Who's used an API key in their code at some point to connect to some service? Yeah, I think, 90% of you? So we know what an API key is. It's a simple, easy way of connecting, authenticating between a client and a server. And it's basically a shared secret. If you have the secret, you're authenticated, you're allowed to access the system. So if our mobile app knows the secret, it can pass it along with the messages, it gets access to the system. The bad guys don't know the secret, they can't get access to the system, they get blocked out. So an API key is a way of authorizing an app access to your services, to the APIs that you're exposing. The challenge we have is in something called reverse engineering. And reverse engineering is all about taking what to the end user seems a locked, sealed application, opening it up and finding out what's inside it, what the secrets are. Secret? Our API key was meant to be secret. Alarm bells should be going off. And reverse engineering, in very simple terms, takes two forms. It takes static analysis and dynamic analysis. And the metaphor that I like here is a mobile app is a book. To the user, the book is closed and it has a little key to stop anyone opening the book. But what the bad guys will do is they'll take the book, they'll open it up, they'll crack that lock, open the book, and then they'll start to read the pages. And that's static analysis, just reading the code within the application. But what they really want to do is go a step further. They want to go to dynamic analysis. So if static analysis is reading the book, dynamic analysis is watching the movie of that book, watching it play out in front of you. So watching that code execute and run and see what it's doing. And actually, they want to go a step further. They don't just want to watch the movie. They want to play the interactive virtual reality video game. They want to prod and poke at the universe that is your application and see what falls out, see what happens as they start to manipulate and play with it. So by going through these different stages from simple static analysis through to actually some very intricate dynamic analysis, you can start to find out exactly what that app's doing, how it's behaving, and what the secrets were that you didn't want exposed in the first place are. So what does that really mean in practice? What does that mean for our API key that we thought was going to authenticate our app and only allow us access to the services and not allow anyone else access to the service? So let's see if this works. Okay, so on my phone, I have a simple application, kind of designed for demo purposes. The application allows me to log in, it connects to the server, sending an API key, and then allows, once I'm logged into the service, I can now order pizza from my favorite takeaway, Pace Pizza. Simple application. The phone it's running on is my personal phone. It's a standard phone. It's got USB developer options enabled. But other than that, the firmware is as it came from the box. It's not rooted. I've not compromised the firmware in any sense. So first thing I need to do as the bad guy, if I want to find the secrets, is get access to the code. At the moment, the code is on the phone, as if it was installed from the Play Store. But with a very two pieces of things, kind of with ADB. Kind of, if you don't know what ADB is, you're probably in the wrong room or the wrong event. So I need ADB, and I need to know the package ID, the application ID, which you'll find on Google Play. That tells me where the application is installed on the phone. From there, if I can type, from there, I can pull that application off the phone, again, using ADB, onto my laptop. I now have the application here. So I now have access to the app that was installed onto the phone. From here, I can use open source tools. My personal favorite is JADX, but there's many others available to decompile the APK. The reason I like JADX is it puts it in a nice graphical window, which is great for doing presentations. And you can see, what are we, 2 minutes into that demo? I now have a decompiled application on the screen, and you can see all the packages that were within that application down the left-hand side. What you can also notice is I've run R8 on the application. So I'm not cheating here. I'm not using anything to make life easy for myself at this stage. Just as you would with your commercial application, we have run the minification over it, which in theory removes useful data from the application. Now, back to the point of this, we're trying to find the API key that unlocks the services, because we're trying to attack the back-end critical infrastructure of pastepizza.com. So we want to find the API key. Now, if you're writing APIs for services, they're generally human readable. You make life easy for the developer that's got to program against them, which means, without too much difficulty, let's see. If I search for API key in my code, it won't surprise you to see it's there. So we found the string API key here. And what we can see is API key is part of this object we're building with the username, password, and API key. It starts to look like a networking message very quickly. We can see just below this, we have a URL, which is connecting to pastepizza.com with a login path on it. So it seems fairly certain, with very quick analysis, we've found the login message, which someone is adding the API key to, which was hard-coded into the application, into the code of the application. So what's 56, AB, etc. So very quickly, we've got to something that looks like an API key. And that's just with static analysis. We could go in and confirm this with dynamic analysis. We could look at the code running. We could put breakpoints. We could sniff the network traffic just to confirm that that is the message we're passing. But it looks like, from some simple messages in the code, hard-coded there, was the API key. And while this is set up as a demo, kind of working with security experts and people that are much more skilled at reverse engineering than me, this is the sort of thing they see every day in real-world commercial applications, and not much more difficult to find than this demo. So our API key seemed to work in theory. We have a shared secret, but it doesn't stay secret for long. So the next step is to use the tried and trusted method of stopping a replay attack. A replay attack is when you just pass the same bit of data every time. The tried and trusted method of doing that is a cryptographic challenge response. And we have a simple but effective approach to that here, where we send our login. The login responds with a challenge, some random number that asks us to sign with the response. Once we sent back the response, we have an authenticated session. So moving to crypto seems the logical step to take next. I'm going to Move to the next part of the demo. So we now have an APK which does that cryptographic challenge response. I could have pulled it from the phone in the same way, but in the interest of time, I've pre-prepared it on the laptop. So we now have an APK that's doing that cryptographic challenge response. So let's start where we found the API key. Let's have a look in the main activity. And if we just scan down through the main activity, we very quickly find the string login, so passing the login message. And this time, what we can see is the minifications not being able to inline the networking code. So login is now passed as a parameter to this K0 class. Wonder what that could be doing. Within this class, if we just look at the imports at the top, we can see a secret key spec being imported. And if we find that in our code, we see it down here. If I was to look at the API code for this class, it's a standard Android API. I can easily find the documentation for it. I can see the first value being passed to it, which here is called bytes. That value, according to the API spec, is the key that I want to be using as part of my crypto operation. So if I just trace back, double click, it takes me to where that's initialized. There's my crypto key that I hid in my code. 1, 2, 3, 4. Yeah, it's not an imaginative key. It's not one you'd use in real life, but it's sitting there in the code waiting to be found. What's really interesting was by complete accident when I was building this demo. In my original Kotlin code, this is decomposed to Java. It was written in Kotlin. But in the original Kotlin code, that crypto key I'd kept far away from the usage point of it. So it's used about 3-4 lines down here. But I'd built that crypto key in my code. That crypto key was far away in a different class elsewhere in the code to try and hide it. The minification, R8, when I ran it across the code, it tried to simplify things, and it pulled the key right where it's being used. It made it easier for me to find and easier for me to demo, which is something to think about. So, if I hit like, we've got a problem. Cryptography is the right solution. Applied cryptography in this example is the right solution, but it's easy to find the keys. So we need to keep those keys hidden. We need to keep them secure. Otherwise, everything we're doing here, 5 minutes reverse engineering, it's easy to undo. It's easy to crack open. That's what this diagram here is showing. If we think about protecting the data stream and securing that, but we also need to think about what's happening in the device and protecting that as well. And one solution to do that is called white box cryptography. White box cryptography is a way of protecting operations and cryptographic operations in this exact environment where things are exposed, things are open, and we can see what's happening. And what white box does is it protects the operation even if you can see every instruction execute, even if you can see every memory read, every memory write. White box will still keep the algorithm safe, and it will keep the data it's processing on safe. So if we applied a white box to what we've just seen, you wouldn't be able to find that key. You wouldn't be able to find the algorithm that was using the key. It would just look like gibberish. It wouldn't make any sense to an attacker, even with extremely powerful and advanced reverse engineering technology. And it's a pure software solution. So it's extremely flexible and puts you as a developer in control. And it's not just theoretical. It's been proven in highly secure markets like payments systems, where I've spent a lot of my life working. So where does PACE fit into all this? As I said, PACE is a software security company. We focus on protecting software IP when it's deployed at the edge. That ranges from our software licensing platform, which is designed to protect and control full applications from piracy, hence the company name, through to targeted tools that are provided to developers that allow targeted protection of individual algorithms, individual blocks of code. And it won't surprise you to learn one of those tools is a white box cryptography tool. And with that, I'll just leave you with the thought that security has to start with the mobile app. We've seen some of the risks if it doesn't. Protecting that app, protecting that code, getting in front of the API can make you, as mobile app developers, heroes of your DevSecOps team. And if you want to move beyond basic obfuscation, please think of PACE. Thank you.